this. Today is the 25th. 9:25. Okay. Velocity can be graphed. You do a position time graph. Remember that V average equals delta x over delta t. On a position time graph, delta x, delta t, what does your slope give you? Velocity. So just like when you graphed circumference against diameter, your slope gave you, we hoped, pi. Here, the slope of that line is going to give you your average velocity. Now, that's great if you have this. So, do any of you have at least one graph in your data that looks something like that? Good! And hopefully it's the car. So it's got a straight line for position time. A straight linear function for position time would indicate what about the velocity? Constant or changing? Constant. And the cars are supposed to be constant velocity cars. Sometimes they are, sometimes they aren't. It depends on if the battery falls out or not. What would that line look like if your velocity was changing? It'd be a curve. And so hopefully, and I've seen two groups that had really awesome data for the marble, where their marble data looked something like that. Most groups can only dream of data so nice, but that's okay. Our methods are primitive. So, though I will say the groups that I've talked to who had the best data, I said, wow, how'd you get such great data? And they said, well, our data looked like crap, so we kept rerunning it. That's kind of what's required. When you get to the inquiry lab that everybody just loves so much, I've had groups who've spent a lot of time rerunning because it's really tough to collect the data I'm asking you to collect. So that kind of attention to method and error pays off. Okay. Okay, so if we've got a constant velocity, it's easy to find the slope of your best fit line for your data, and you get a pretty good approximation of the average velocity of the object. But if the object is moving, if you have a line that looks like this, or heaven forbid, like that, can you find a single slope? No. And I think my percentages are about the usual this year, where about half of you are in calculus and about half of you are in advanced math, and that's fine. I've had years where I had a quarter of the class who hadn't even had advanced math. They had gone from algebra 2 to stats, and that's okay. If you're in calc, have you done derivatives yet?
No.
Okay, well, never mind then. We'll talk about that after you've done derivatives. So you can't find the slope of the whole line, but you can find the slope of a point on the line by finding the slope of the tangent to that point. And once you get a little further in calculus, you'll find that, in fact, the first derivative gives you that, and it gives you a way to find the slope of a point. We don't do that in here. We don't have the mathematical tools as a group to do that, but I want you to understand that that's how it would work. So if you have a car that is traveling, from here to Rogers, and you start off slow, and somebody who jackrabbits the gas is going to do this, and then maybe they slow down again. I'm sorry. Nope, Moser. There. Okay. So they slow down. And then what's happening in this portion of the line? Tell me about their velocity. So this is a position time graph. Position time. So let's break this into a few chunks. A, B, C. And having this on graph background works really nicely. So at your table, discuss, come to agreement. Is there any portion of this line where their velocity is 0? Talk to one another. Okay, good. I hear lots of muttering about C, and that's what I want. The reason that I have you guys talk to one another rather than yelling it out is neurologically, here's what happens. If you're the kid who didn't have enough coffee this morning, or you're just feeling a little slow this morning, and the first person who yells out the answer, your brain stops working. And then you don't get the benefit of processing it for yourself. So that's why I'll have you talk to one another first, so that we don't, no, it's okay, so that we don't shut down brains. So, yeah, why is the velocity 0 at C? Talk to one another. You can go talk to them if you want. I know you're missing your buddy. Okay, I'm hearing good mutterings. Oh no, we're not there. You're leaping the shark, the whale, the barrels. I don't know what you're leaping, but you're leaping. We'll get there. Tomorrow we'll get there. So what are we tracking on the y-axis? We're tracking delta x. We're tracking change in position. There is no change. Other than bad drawing, there's no change in position in segment C. This object has stopped moving. It is no longer changing its position. What's the slope of that portion of line? Tell one another. What's the slope of that portion of line? 0. Yes? The slope of portion C, slope here, equals 0. Hey, what did we say the slope is equal to? Velocity! I know, I just keep pulling the rug right out from under you. You think you want one thing, you want pain in the tuchus. The slope is equal to 0, therefore during that interval the velocity is 0. That's an easy way to look at that. So I'm going to plot the motion of an object, and we'll do some line segments. And I want you to tell me things about its velocity. So, okay. Now let's segment that line a little bit. Okay, so here's what I want you to do at your table, talking to one another. At what segments of this line is velocity constant? Give me a segment, you guys. Give me one segment where you think it's constant. Just one. A, okay. Who would agree with them? Me too. Okay, give me another segment where you would say it's constant. Any other one you picked than A? Who would agree? Me too. Does any group have more than A and B? Excellent. Give me the third segment that you would say is constant. E. Well, hold on. If I do, I would disagree with you as E was written. I would agree with you now, and we could chalk that. The only reason I moved that is because, yeah, it was sort of intended to be constant, but bad drawing and bad line segmentation. So, okay, A, B, and E. Anybody else see any other segments where you would argue that the velocity is constant? Yes, ma'am.
You would argue F.
You would argue F. Okay.
I mean, it's kind of like slope doesn't help. Like
well, you know what? And I would mostly buy your argument, especially before I press section E.
Yeah,
before I messed around with it. If we said that F was from here to here, and there's still a little bit of a curve, but it's pretty close. So you're all seeing, whether we're going to quibble about bad drawing or not, or have to move endpoints or not, you can see that if the line's straight, the velocity is constant. Now, the next question I have for you. At your tables, talk this over. Number 2, where is the velocity positive? So the slope of that section is positive. Does it matter that the position is in negative territory? No. Does it matter that the object is moving back towards whatever your arbitrary 0 mark is for position? No. What matters is that the slope of the line is positive. Okay, one other segment. Which table? Let's see. Did I hear from your table early? No, I got you guys. Okay, you guys. Give me one other segment where you feel strongly that the velocity is positive. A. Okay, why? Positive slope. Yeah, positive slope means the velocity is positive. Give me, let's see, are there any other sections? No, there are not. Does anybody else have any others? You want to make a compelling case for one that isn't there? Okay. So the sections of line, therefore, okay, let's talk about why velocity is positive here. The velocity is final position minus initial position over final time minus initial time. Well, that's also rise over run. Final y-axis position minus initial. So in this case, this is, so let's make up some coordinates. Well, it's origin. So we'll say 4 minus 0 over 1, 2, 3, 4, 5, 6. 6 minus 0. So slope of that section is approximately, what, 2/3, so approximately 0.66. And this would be in meters per second. Pretty slow. Pretty creepy little object. Creep, 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 creep. But it's a positive velocity because in each case, our final is larger than our initial. Let's look at segment B. Cut. So for segment B, final on the y is about 1. Initial is 4. Final on the x, oh, I really should have labeled these. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus, did we say that was 6? 9 minus 6. So we have negative 3 over 3. Wow, I couldn't have done that better. So we have a slope of negative 1 meter per second. The object's moving, it's moving at constant velocity, yet it has a negative velocity because of the direction it's traveling in. This is that thing about does direction matter, the fact that velocity is a vector. Direction matters because we know that that negative velocity in segment B, if we think about it in terms of progress, is essentially going to cancel out any distance that this object covered in segment A. It's almost back to origin. It's almost back to our 0 mark. Does that make sense? And let's look at section D. Let's look at section D here. So is the velocity positive or negative? By now you can all do this like that. It's negative because the slope is negative. Now it's not a constant velocity. We could do a tangent line. We could do some sort of weird averaging. But here's the question. It has a negative velocity. Is it traveling towards or away from the origin? Still traveling away from origin. So if we're imagining that origin is home, it's still getting further from home. It's getting places. It's just getting places with a negative velocity. Okay? So one of the skills that you're going to build here is recognizing what a position time graph means in terms of velocity. And yes, you'll see some quiz questions like that, test questions.